Welcome back to Dave Does Math from Home. This is part 2 of our video series on section 16.3, where we're doing double integrals in polar coordinates. Because trying to do double integrals of round things over round regions in square coordinates was a huge mistake. So we're doing double integrals of round things in round regions using round coordinates, and it's much, much, much nicer. So we ended off with a discussion of pirate integrals. dA is r dr d theta. So I'm going to add that here to our list of really important formulas to remember. Instead of dx dy, we're using r dr d theta. The pirate joke really only works if dr is the first thing of these you do. So some of you might be wondering, what if I use r d theta dr? And you can do that. There's nothing stopping you from doing that. It's just sort of not conventional. Mostly because it's a lot less fun to say. It's fun to say r dr d theta and then just pretend you have a pirate integral. It's not fun to say r d theta dr. That's much too mathy. The good news is, because we're doing round regions using a round coordinate system, we are pretty much always going to be using constants as our bounds of integration. And so in that sense, it sort of doesn't matter which order you put these in. For these guys, when we were doing section 16.2, the order mattered a lot because one of our sets of bounds, the inside set of bounds, had to be based on functions so that we could get those weird shapes. These are often called polar rectangles just because it's all constants in the bounds, and that's what we want. So basically, almost all the time, we're going to be using these constants in the bounds. It's going to be nice. So I think at this point, there's still more to say about these bounds, and we'll get to that later. But at this point, I just want to finish this polar integral so that we can have at least one example done. First thing I'm going to do is simplify this, as I alluded to earlier. We're going to be integrating the function r cubed dr d theta. And r is going from 0 to 3, and theta is going from 0 to 2 pi. And the integral of r cubed is 1/4 r to the 4th, evaluated at 0 and 3, d theta. So this will be the integral from 0 to 2 pi of 81/4 d theta. The integral of this is theta, 81/4 theta. We plug in 0, we get nothing. We plug in 2 pi. You're basically just multiplying this number. When you get to this point, usually, typically, generally speaking, when you get to this point in the integral, there's probably not going to be many thetas left at all. You're usually just going to have a constant here. And if you're integrating a constant from 0 to 2 pi, that's the same as multiplying it by 2 pi. So this will be 81 pi halves. So this is the good news. Once you get this thing set up, evaluating it is effortless. This took, what, 30 seconds? Maybe more, because I was talking about integrating constants. This goes really, really fast and really, really easy once you have it set up. So the challenge here is going to be getting it set up, sort of getting your mind wrapped around the idea of doing integrals in polar coordinates with r's and thetas all over the place, and especially r dr d thetas. That's going to be big. Imagine trying to get 81 pi halves out of these square roots. Like, where's the pi going to come from? I think the only way to do this in rectangular coordinates involves an inordinate number of arc sine trig substitutions. And no one wants those because no one likes those. So we're just going to do it in polar coordinates instead, and it's going to be really nice. I'm going to erase all of this. I want to talk very briefly about coordinates and regions and what those things look like. And then I want to do some more examples. So earlier I mentioned polar rectangles. And so the idea of polar rectangles are things like our filled in circle is sort of the most basic form of polar rectangle. Polar rectangle just means that the bounds in polar coordinates are constants. Remember when we did bounds, when we use constant bounds in rectangular coordinates, we get rectangles. So rectangles are sort of easy mode for these evaluating these integrals, and that's why when you have constant bounds, even on a polar integral, we still jokingly call them rectangles because they're constant bounds and they're easy. But they don't look like rectangles, which is why I want to talk about some stuff. Imagine we have a region where R is going to go, let's say R is going to vary between 2 and 4, and theta is going to vary between negative pi over 4 and pi over 4. So that means we're going from negative pi over 4 to positive pi over 4, and R is going from 1, 2, 3, 4. R is going from 2 to 4. This region here is our polar rectangle. So it's not always circles. It's always going to be like sections of circles. But it might not go all the way to the origin. Like if R starts at a number that's not 0. If R starts at 0, then it's all the way into the origin. And it just ends wherever R is. But we can choose to not start at 0. We can start a little further away from 0. And we don't have to go the full 2 pi full circle. We can do however much or little of a circle we want, starting from wherever we want. And we can start the radius and then the radius wherever we want. So this is a polar rectangle. It's like if a rectangle got wrapped around something. They're pretty neat. They're handy. There'll be some questions on the homework about sketching graphs of these regions. But sketching graphs just means choosing the multiple choice option that matches. So that's about as complex as our regions are going to get. Mostly they're just going to be circles. So let's talk about evaluating, find the volume beneath e to the negative x squared minus y squared. Not under, let's go over. Over the region let's do a circle of radius 4. So, if we wanted to set up this integral in rectangular coordinates, the rectangular coordinate version of this integral is we're integrating e to the negative x squared minus y squared. We can do dx, dy this time, it doesn't super matter. X would go from negative square root 16 minus y squared up to positive square root 16 minus y squared, and y would go from negative 4 to 4, and looking at the bounds by themselves is a little horrifying. These square roots are going to make things really catastrophically messy. Even if we don't look at the bounds at all, if the only thing you're looking at here is this function, that should also indicate to you that this is a terrible idea because this function is not integrable. This is a composite function. with x squareds and y squareds on the inside of an exponential function, and there is no other function that I can use to do the substitution. So this is just a huge bummer that we can't do in rectangular coordinates, which is fine because we can do it in polar coordinates and it gets really easy. I'm going to factor out this negative. Minus x squared minus y squared is the same thing as minus x squared plus y squared. So this is a really easy substitution for r squared. And this is sort of like a, I guess I should mention, on tests and quizzes, like when you're doing the homework for this section, you can be reasonably well assured that every single problem in the homework for this section is something you should be doing in polar coordinates, because it's the homework section about integrals in polar coordinates. So no surprises there. On tests and quizzes, I'm not going to tell you which coordinate system you should be using. So I'm going to just give you an integral. I'm going to give you a function and a region. I'm going to say find the volume of this function in this region. And you have to decide whether you're going to use polar coordinates or rectangular coordinates. And there's two really, really big hints. If your region is a circle, please use polar coordinates. If you have x squareds and y squareds, specifically x squareds plus y squareds, in your function, you should probably be using polar coordinates, because x squared plus y squared is just r squared, and that's much, much, much easier to deal with most of the time. So, this is an excellent example of how not to do this problem. And if you're taking the quiz and you start to set it up in rectangular and you're like, God, that's ugly, like, there's nothing lost here. We can scrap this and immediately start the rectangular one. So, no worries there. I'm going to erase this to start the rectangular one. In rectangular coordinates, the function we need to integrate is e to the negative r squared. The dA we're stapling to the back of this is r dr d theta. R, if the region is the circle radius 4, r goes from 0 to 4. And theta, if we're doing the full circle, is going to go from 0 to 2 pi. This is much, much, much easier. Hopefully everyone has had a chance to review their integration by substitution techniques and is now once again a master of that. Some review from Calc 2, section 5.5, doing integration by substitution. The short version is, this is a substitution integral because it's a compound function. I need a negative 2 in here so that it matches the derivative, and to do that I'm going to put a negative 1/2 on the outside. And then this thing just integrates into e to the negative r squared. So I have negative 1/2 theta still goes from 0 to 2 pi, e to the negative r squared at 0 and 4, d theta. So e to the negative 16th minus 1 e to the negative 16th minus 1 d theta. And again, this looks a mess, but it's secretly just a constant. When you're integrating just a constant d theta from 0 to 2 pi, you're just multiplying it by 2 pi. So this is negative 1/2 times 2 pi times e to the negative 16th minus 1, which we could clean up a little bit by saying these guys cancel, the 2 and the 1/2 cancel, and I'm going to use the negative to switch the order of this subtraction. So I'm going to say that this is pi times 1 minus e to the negative 16th power, which is just a tiny, tiny, tiny bit less than pi. And that's it. That's your answer. That is how to do an integral in polar coordinates over a circular region. I have one more example to do, but I'm not going to start and finish it in the next 5 minutes, so we're going to move on to part 3 of this video. Stay tuned.